Hello everyone, my name is Zhongli Zhu. I'm a PhD student at UC San Diego, and I am very honored to give the talk here about our recent work, Consistent Range Approximation for Fair Predictive Modeling. This work has been done in collaboration with Sam Gahotra, Nazanin Sabri, and Babak Salimi. Algorithm decision making has become increasingly prevalent across many domains, including recommendation systems, finance, criminal justice, and more. These algorithms seem to perform amazingly in the above examples, but still, we may think about, are these algorithms perfect? Here we can take a look at this example. This man is complaining about the algorithm of the Apple Card that determines the credit limit. So he and his wife have been married for 20 years, they file the joint tax returns, and they live in a community property state. But still, he got a much higher credit limit than her wife. And as we can see, at least for this individual case, this algorithm is actually very biased. And this is not the only case. Here are more news showing the fact that there are many biased algorithms used in decision making. We may take a look at this simple ML pipeline presented here, which summarizes how the ML models are obtained and applied. Now, due to some reasons, the model is unfair and make biased decisions. The user will observe the bias. However, during deployment, it is impossible to look into every specific case and see if that decision is fair. It is critical to think about how can we quantify or measure the unfairness of a model. In general, we expect the decision made by a fair model is independent of the protected attribute S, conditioning on some other variables. For instance, in making hiring decisions, we want to have decisions independent of the gender given same level of skills. This corresponds to the popular fairness notion, the conditional statistical parity. This is a definition that generalizes other popular fairness notions. So when A is the empty set, it becomes the statistical parity, and when the admissible variable A contains only the target Y, it becomes the equality of odds. Based on this notion, we defined our fairness query to evaluate the degree of violation of the conditional statistical parity. This can be computed from the aggregate group by queries. Now going back to the ML pipeline, now that we have this fairness query to evaluate models' unfairness, we may wonder, can we audit or further mitigate models' unfairness during the model's training? So there are mainly three kinds of existing algorithmic fairness techniques that try to train a fair model, which is pre-processing, in-processing, and post-processing. Especially for the in-processing algorithms, we can obtain this constraint optimization problem, where we try to minimize the empirical loss, which penalizes the misclassification cases. And we have the fairness constraint here to ensure that the model is fair on the training distribution delta. Going back to the ML pipeline, we usually call the gray parts as the deployment stage, meaning that the data used for the training and the data used for decision making can be different. And we assume the data used for decision making in the deployment stage come from the target distribution omega. So going back to the optimization problem, the constraint guarantees the model to be fair on the training distribution delta. However, does this guarantee the model to be fair on the target distribution omega? Obviously, the answer is no. Actually, this optimization only works or say successfully mitigates bias during these deployments only if two distributions are identical. In other words, if this critical assumption does not hold, a model that is fair during training and validation stages may not guarantee to be fair on the deployment stage. But it is obvious in practice this critical assumption often does not hold, and the distribution shift will exist. This distribution shift will further making the fairness query evaluated on the training distribution and target distribution to be different. Therefore, a fair model on the training distribution does not directly imply a fair model on the target distribution. The distribution shift can result from several reasons, such as data quality issues. Among many data quality issues in this work, we are especially interested in the selection bias. It is always happening in the real-world scenarios, and it is one of the major causes of distribution shifts. Now let's look at a concrete example to see how this non-randomized selection can affect model's fairness. Here, the dependencies between the features can be described by this causal diagram below. It essentially shows how the data is generated in practice, based on domain knowledge. Now we assume this dataset suffers from the selection bias. The red records correspond to the selected samples, and the newly added column C is the indicator of the selection. In this example, the selection bias can actually be modeled by the data collection diagram, where we just add the selection variable C to it. If we condition on the selection variable C, we will notice from the causal diagram that the correlation of features will be changed. This is indicated by the red dotted line in the causal diagram. The change in correlation is also reflected in the joint distribution of age and target Y on the right side. The age and target Y was uncorrelated in the entire complete data, but turned out to be correlated in the incomplete data due to the selection bias. The intuition of using causal diagrams to model the selection bias is that in practice, we usually cannot actually complete the missing part of the data. But we have a sense about what are the major causes of selection bias, namely the parents of the selection variable in the data collection diagram. Here, if we train a classifier on the red selected records, we will get a biased classifier that makes decisions not only based on crime type, but also based on the age. This classifier is fair and accurate on the selected samples, but inaccurate and unfair on the entire data, because it learns the correlation between the age and target Y. This correlation is caused by the selection bias, and it does not exist in the entire complete data. Therefore, a classifier using age to make predictions will be biased when evaluated on the complete data. We just showed that selection bias can be modeled using the causal diagram, and we can complete the ML pipeline with data collection. In the previous example, we learned that using only the training data cannot train a model that is fair on the selection bias. Here we may have two follow-up questions. What other information can we leverage to train a model that is fair under selection bias? And further, how can we leverage those information to train a fair model under selection bias? Here we introduce some popular works in the domain of fair ML that answer the questions. In general, some works try to utilize the samples from the target or deployment distribution, while others incorporate the causal diagram. The major weakness of the first line of works are that they are just restricted to covariate shifts, which does not generalize all kinds of selection bias, and they require unbiased samples, which are hard to require in practice. While the causal-based methods make assumptions about the causal diagram because they need the causal diagram to be addressable. However, this assumption is also difficult to hold. To fill these gaps, we have recently developed a system called GRAB to address the challenge of selection bias in predictive modeling. With this system, it is possible to build models that are certifiably fair on the target population, even when no or limited external data source is available during training. The main idea is to approximate a model's unfairness on the target distribution using available information and biased data by drawing inspiration from consistent query answering techniques used in databases. The key point is that query answering from biased data is similar to query answering. The key point is that query answering from the biased data is similar to query answering from incomplete and inconsistent databases. By leveraging these insights, we can use the GRAB system to build predictive models that are more fair and robust to selection bias. Going back to the questions, what information do we use and how do we use it to train a model on the selection bias? As we show here, we will be using the data collection diagram, and now let's see how we will use it. As mentioned, the data collection causal diagram encodes some information about the target distribution, which is what variables are direct causes of the selection bias. Here in this example, the direct causes are the variable z and zip code. This information encodes the conditional independence condition, as we show here. We can leverage this conditional independence to find the agreed or common information shared between the biased distribution delta and the unbiased target distribution omega. So roughly the steps are, first we have the data collection diagram. We obtain the conditional independences from the data collection diagram, and we use this conditional independence to find the statistical properties of the target distribution that is shared with the biased training distribution. Note that in order to get the conditional independence conditions, our approach only requires knowing what variables are affecting the selection, but does not require to know how the direct cause variables affect the selection. For example, the selection probabilities. However, we will further show that knowing how they affect can actually improve our solution quality. After obtaining the statistical properties of the target distribution that is shared with the biased training distribution, we will discover our problem is analogous to consistent query answering on inconsistent databases. We all have incomplete data, we all have some, but not all properties of the clean data, and those properties restrict the space of all possible clean data. Finally, since we don't know the entire clean data, we all want to bound the query answers based on the partial available information about the clean data. Now I will illustrate our consistent range approximation framework. Here, the ML model, the data collection diagram, the fairness query, and bias training data form the input component of our system. Based on these components, we will have the possible repairs, which stands for all possible ways to complete the original biased training data. After applying the fairness query on all possible repairs, we will get corresponding possible fairness query answers. We can further conclude the possible query answers to obtain the consistent range, which includes the consistent lower bound CLB and the consistent upper bound CUB. Once we get the consistent range, we may wonder, can we further improve the bound and get a tighter bound? The answer is yes. So we can incorporate external data sources to tighten the consistent range. The external data sources can include ChatGPT, the Statistical Atlas, which is a public census data website, and the United States Census Bureau, etc. The external data sources and the data collection diagram form the auxiliary information that impose constraints on possible repairs. This is because the auxiliary information includes statistical properties of the target population, which the complete clean data must have. When more statistical properties are revealed, the number of possible repairs will reduce. At some point, the information included in the external data source will be sufficient for us to directly approximate the fairness query answer on the target population, rather than its upper and lower bounds. We already showed what information we will incorporate, and we will utilize the statistical properties of the target distribution. Before we look at how exactly we will use them, we can conclude the challenges we face. So we know the information about the data collection process and the external data sources provides us the statistical properties of the target distribution, and that limits the space of possible repairs. However, characterizing the space of all possible repairs is still a challenging task, making computing the consistent answers a complex process, because there will always be a large number of possible repairs, and it is impossible to materialize all the repairs and find the consistent answers afterwards. To address this challenge, our method provides a closed-form approach to compute the consistent upper and lower bounds for fairness queries. And now we will present how exactly we utilize the statistical properties, namely our closed-form solution. As mentioned, our approach is also able to incorporate various levels of external data, and here we conclude our approaches that corresponds to different levels of access to external data source. Now we will use experiment results to show the effectiveness of our approach. We test our approaches on 3 popular datasets, and we compare with 2 preprocessing baselines and 3 in-processing baseline methods. Among 4 in-processing baseline methods, the Cortis and Rezai correspond to methods that also uses external data to help ensure a fair model on the target population. We first compare our methods in the setting that we have no access to the external data source. Here, the blue point refers to the original classifier trained on the biased training data, and the red point refers to the original classifier trained on the unbiased test data. The 3 methods below are baselines that do not use any of the external data source, and the purple skyline corresponds to our method. This skyline represents the F1 scores and unfairness of models trained with CRAB. Different points in the skyline correspond to different upper bounds, namely different unfairness requirements. When there's no requirement, the skyline overlaps with the original classifier. This comparison plot shows that our method is most fair and accurate on the synthetic data. We also compared on the real-world adult data. The left plot refers to the setting where no external data is used, and the right plot refers to the setting where external data is incorporated. By comparing the left and right plots, we can conclude that external data sources actually help preserve the model's accuracy. And by comparing inside the plots, the CRAB methods turn out to be the most fair and accurate. We also examined the effect of selection bias in the HMDA datasets for 2 parishes in Louisiana. Here we used the ratios obtained from the public websites as external data source, and we used them to successfully train a fair model. So in conclusion, data quality issues can significantly impact fairness in machine learning, and in practice, training data is always biased in one way or another. Existing fair ML models cannot properly handle unfairness due to the existence of selection bias, and we discussed our approach that draws inspiration from databases to build models that are certifiably fair in the presence of selection bias.